All right, today we're going to crack open one of the most powerful tools in your entire geometry toolkit, proving that triangles are similar. Now, I know, that might sound super textbooky, right? But trust me, this one idea is absolutely fundamental. It's how we build, how we measure, and really, how we understand the world around us. So let's just dive right in.
You ever look at something massive, like this bridge, and just wonder how on earth they know that would work? Well, a huge piece to that puzzle is similar triangles. See, before engineers build the real thing, they can create a small-scale model that's perfectly similar. And by understanding those proportions, they can figure out all the forces and lengths they need for the full-sized, real-deal structure. It's pure geometry in action.
But here's the catch. The official definition of similarity, well, it's kind of brutal. It requires you to show that every single corresponding angle is congruent and that every single corresponding side is proportional. For a triangle, that's 6 different things you have to check. 6. There has to be a better way.
And don't just take my word for it. Here it is right from the source material. Using that full definition is, and I'm quoting here, almost impossible to use as a method of proof. I mean, just think about it. Trying to measure and compare every single side and every single angle perfectly, it's just not practical in the real world.
So that's the big question, isn't it? If the by-the-book method is basically a dead end for proofs, how do mathematicians and engineers actually get this stuff done? Well, thankfully, they came up with some really clever shortcuts.
And this is where we get to the good stuff, the smart way. We're about to add 3 incredibly powerful tools to our geometry toolkit. These are the postulates and theorems that let us prove similarity with way less information. You can really think of them as the ultimate geometry cheat codes.
First up, we've got the most common, and you could argue the most useful shortcut of them all. Angle-angle, or just AA. It is beautiful in its simplicity. If you can show that just 2 angles in one triangle match up with 2 angles in another, that's it. Game over. You're done. The triangles are similar. Because think about it. If 2 angles match, the third one is forced to match too, right? This saves you a whole step.
Okay, next up is side-angle-side similarity. We write it as SAS with a little squiggle, a tilde, to show we're talking about similarity, not congruence. Now, the key thing to remember here, the absolute most important part, is that the congruent angle has to be the one that's sandwiched right in between the 2 sides you're checking. So, you need one matching angle, and you need to show the 2 sides that form that angle are proportional to the corresponding sides in the other triangle.
And our last shortcut is side-side-side similarity. This one couldn't care less about angles. If you can just show that the ratio of the corresponding sides is the same for all 3 pairs, like say every side in the big triangle is exactly double the length of its partner in the little triangle, then you have proven they're similar. Simple as that.
Okay. Theory is great and all, but let's actually see how this stuff works in the real world. We're going to take one of these shortcuts for a spin and solve a classic geometry proof step by step.
All right, here's our challenge. We've got this kind of hourglass shape, right? It's made of 2 triangles. Now, the only piece of information we're given for sure is that the top line, AB, is parallel to the bottom line, DE. Our mission, should we choose to accept it, is to prove that the top triangle, ABC, is similar to the bottom one, EDC. Let's see which shortcut can help us out.
So, for step 1, let's use that one clue they gave us, that lines AB and DE are parallel. You see how the line AE cuts across both of them? We call that a transversal. And a fundamental rule in geometry is that when this happens, the alternate interior angles, in our case, angle A and angle E, are congruent. They're equal. Perfect. That's one pair of angles. Checked off the list.
Now we need a second pair. So look right at the center where the 2 triangles kiss. Angles 1 and 2 are what we call vertical angles. They're made by 2 straight lines crossing. And another core rule of geometry is that vertical angles are always congruent. No exceptions. So we know for a fact that angle 1 is congruent to angle 2.
And boom, just like that, you see the incredible power of our shortcut. We found one pair of matching angles in step 1, and we found a second pair in step 2. That is all we need. So now we can say with total confidence, triangle ABC is similar to triangle EDC. The reason? Just 2 letters, AA. Proof complete. So much easier than measuring all 6 parts, right?
So, why did we do all that work? Why do we even care about proving triangles are similar? Well, because proving it isn't the end goal. It's actually the key that unlocks a super powerful ability, the power to find missing lengths and solve for the unknown.
This right here is the grand prize for all our effort, CSTP. It's a bit of an alphabet soup, but it just stands for corresponding sides of similar triangles are proportional. Once you've used AA, SAS, or SSS to prove two triangles are similar, you earn the right to use this powerful concept.
So check it out. This is what CSTP lets us do. Once we know for a fact that this inner triangle is similar to the outer one, we can set up proportions. We can say that the ratio of side HJ to side SR is exactly the same as the ratio of side JK to RT. So if we know 3 of those lengths, we can use some pretty basic algebra to solve for the missing one. This is exactly how you can measure the height of a huge building just by measuring its shadow on the ground.
All right, let's do a quick recap of the awesome new tools we just added to our problem-solving toolkit today.
And here they are, in all their glory. Your 3 go-to shortcuts for proving triangles are similar. You've got angle-angle for when you can find 2 pairs of matching angles. You've got side-angle-side for when you have proportional sides wrapped around a matching angle. And you've got side-side-side for when you know all the sides are proportional.
And let's never forget why any of this matters. We started with this bridge, and we're ending with it. The ideas we talked about today, they're not just for passing a geometry test. They are the mathematical bedrock that allows us to design, to build, and to understand the scale of our world, from the tiniest computer chips to the most massive structures imaginable.
So the next time you're out and about and you see the shadow from a tree or the beam of light from a projector or even the design of a roof, I want you to think about the hidden triangles. Because now that you have the tools, you won't just see shapes anymore, you'll see the actual geometry that holds our entire world together.